Okay. So chemistry is the study of matter, its properties, and its transformations. Matter is anything that has mass and takes up space. We perform chemistry up in the laboratory, so making measurements correctly is important. So we spent time on Thursday. And we would look at, for instance, we had a graduated cylinder. And we figured out that with the graduated cylinders that are upstairs, we could only measure to 1 decimal place. Basically, we came to this conclusion because we thought about it and we were looking at the, we looked at each place within a number to determine whether we could say with certainty what that spot was. So in other words, we were asking ourselves, is there a line for every one's place? And yes, there is a line for every one's place. And then we asked ourselves, is there a line associated with every 10th place? Meaning, was there a line at point 1, a line at point 2, a line at point 3? And we found out that no, there was no line at 0.1 or 0.3 or 0.5. Because there was no line for the 0.1, 0.3, and 0.5, and so on, then the 10th place was our estimated digit. So that is why we would only measure to 1 decimal place with our graduated cylinder. Any questions? Now, the next thing we need to talk about, though, is this uncertain digit. Every measurement has an error associated with it. These errors can be described as random errors, or they can be described as systematic errors. What it boils down to is, do you have any type of control? Can you alter anything in order to alleviate the error? Random errors are just that. They are random. They are not due to a single issue. They cannot be controlled. The second type of error is a systematic error. Systematic errors are errors that can be eliminated by the scientist. These errors tend to be, for example, incorrectly reading a device, or not following directions, or having a dirty balance, or something else. Basically, there are things that you have some control over. Whereas these random errors, you have no control over. Random errors include things such as electrical fluctuations. You can't control the electricity that comes into the building. So when it hits those balances, there's a chance that you're going to have electrical fluctuations, and it's due to the electricity coming into the balance. Now, if your fluctuations occur due to not having that glass lid on, that's your fault. Or leaning against the table, that's your fault. Or something like that. But as long as it's due to electricity, that's something you couldn't control. Another random error. If everybody is looking at the device correctly, which when you're looking at a graduated cylinder or another item that measures a liquid, to look at the thing correctly, your eye should be on the same level as the bottom of the meniscus. If your eye is not at the same level as the bottom of the meniscus, then the error is your fault because you are not reading the device correctly. Because it has to be here, or we can get what's called a parallax error. That's something you can control. But now, if you and your partner are doing, if your eye is at that level, and you read it as 3.1 and I read it as 3.2, technically they can both be correct, because as long as our eyes are at the correct level, you can't control my opinion. And I can't control yours. So that opinion piece is a systematic error, as long as you're doing as long as you're at the correct level to make the measurement in the first place. Now, usually with the 10 mil grad cylinder, we don't have that issue. But once you get to the burette, you're going to find that you and your partner may disagree slightly. It's okay if it's only a slight, and it'll always be a disagreement in the uncertain digit, because that's where the error is going to occur. Now, to let people know that we have an error, we can use, we'll record our value plus or minus an uncertainty. And I am going to lose this. Oh, okay, I'll go as long as I can, then we'll see what I have to do. Now, with respect to this uncertainty, and number one, you look at your instrument either way. Sometimes the uncertainty is on the instrument. it will be, you will know that it's the uncertainty because again, it will follow this plus minus that you will see on the instrument itself. But what happens if the uncertainty is not on the instrument? Well, then what you need to do is ask yourself, is this an analog device or a digital device? Basically, with digital, we're talking an electronic device. I'm going to start with the electronic device because it's easier than the analog device. Let's say I have my balance here. That does not look like a balance. Anyhow, I have my balance and it reads 1.236. The measurement would be 1.236, but the uncertainty, you're going to simply take and put a 1 in the last decimal place. So because this unbalance read to 3 decimal places, the 1 goes in the 3rd decimal place. If I had a device and it only read 1.06, then I would record the 1.06, but I would put a 1 in the last decimal place for the error. And as you get upstairs, unless you have air fluctuation, unless you have somebody leaning on the table, unless you have crystals, typically it's the last decimal place that tends to fluctuate the most. Now I'm going to go back to the analog. Analog is anything, is almost, it's all of our glassware. All of our glassware would be considered analog because it's not, you don't have a digital display. To get to the analog, what you do is you take the difference between adjacent tick marks or lines and divide by 2. And that will equal what you record as your error. So going back to my poor display for a graduated cylinder. Yes, I know I'm about out of energy. This was our 10 mil graduated cylinder. Say that my liquid is right here. I would record this as 1.6 for the measurement because you always read at the bottom of the meniscus. And now I need to figure out the error. So I'm going to look at 2 adjacent lines. The difference between those 2 adjacent lines is 0.2. To get the error, you're going to take that 0.2 and divide by 2. So your error comes out to be 0.1. If I were to have a beaker, again, to figure out the error or the uncertainty, I use those terms pretty much interchangeably. There is a difference between them, but I use them interchangeably. And a lot of people will. You're going to look at two adjacent lines, figure out the difference. The difference is 50 milliliters. You're going to take that and divide by 2. So this would be a plus minus 25. Any questions about how to get the error? Because you're going to be required to get the uncertainty error in lab this week. Yes.
Are the adjacent lines not relevant to the meniscus? Like, is it just whatever is labeled?
It doesn't matter where it's at relative to the meniscus because it's the error associated with the device. So if I had in that graduated cylinder 7.5 mils or 7.5, it still would have been a plus or minus 0.1 because it's associated with the graduated cylinder, not with the actual measurement you're making. Questions? Okay, so the last thing I'm going to discuss with respect to a measurement is, and it's associated with your laboratory, but it's also the reason we are so persnickety about significant digits. Is the concept of accuracy and precision. I could give you the definition to separate accuracy and precision, but one thing that helps me keep accuracy and precision separated is accuracy begins with an A. So accuracy means you get an A because you got everything perfect with what the substance should have been. I mean, if you're thinking about that on a target, means you hit the bullseye. Accuracy on a test gets an A because you got everything correct. You hit the bullseye. Now, precision just means that all measurements are close to one another. They can be way off the target, but as long as they're all relatively close to one another, that's precise. You're precise. It's just way off the target. Folks, the only way to get to the target is calibration. Now, we can get close, but it doesn't mean we're going to hit the target. The only way for us to probably get the target is the calibration. If everything is calibrated and we're using top of the line instrumentation. But we can obtain precision fairly regularly. As long as you're performing the experiment correctly and looking at the device correctly, you should be able to get to precision. Now, we do have instruments that help us inch closer to the accuracy. So how could we inch closer to accuracy? We can choose an instrument that reads to a greater number of decimal places. And the reason, and all this gives us greater precision. And if it's calibrated, it would also give us greater accuracy. But it's going to give us greater precision for certain because you're going to see that the measurements, I can't even spell today. Are able to be read closer together. Last week, we looked at a burette compared to the graduated cylinders. All of our graduated cylinders read to only 1 decimal place. Burettes read to 2. Because a burette can be read to a greater number of decimal places, you're going to be able to get all of your measurements closer together. And so a burette is going to have much greater precision than would a graduated cylinder. Questions? So when I say read to a greater number of decimal places, if you'll recall on the graduated cylinder, I had to estimate the first decimal. But on a burette, I'm estimating the second decimal. So I know that first decimal. I know what it is. I just got to estimate the second decimal now. Yes, a burette would be plus or minus 0.01. So it'd have 2 decimal places. Significant digits matter, folks. Number of decimals we can record matter because it tells us the accuracy that we can get our measurement, it tells you the precision to which you can make your measurements. It tells the reader something about your instrument. So these significant digits matter. So my iPad is about to die, unfortunately. Thankfully, I'm the only one on, but I will post this piece, but I am going to have to go to the board for the remainder because I goofed and did not bring my charger. I will do a better job.